an organization that has put so much into the educational sector. We run several programs which include A-Level, your IGMB and JUPEB, O-Level programs, Post UTME lessons, which is also ongoing presently. You can also check the above for contact details, and also during the process of this video, the website will be streaming underneath. Okay, today I will be taking organic chemistry. And under this, I shall take several topics which include resonance and tautomerism. And I shall also be taking isomerism. I hope you enjoy these topics, and also if you need more details, you can follow us on our A-Level program. Also, admission is ongoing concerning that part. I shall start with my first topic, resonance and tautomerism. So we'll begin with resonance and its definition. They are actually two very different topics, but then they are taught together because of certain similarities between them. So resonance definition, it can be defined as the delocalization of Pi electrons. The word being present is delocalization. This word delocalization means a process whereby a material moves from one point to another without having a certain position. So basically, resonance is the delocalization of Pi electrons or Pi bonds. We all know that for every Pi bond, there's two Pi electrons. You have carbon to carbon double bond and carbon to carbon triple bond. Carbon to carbon single bond does not have a Pi bond. It only consists of one sigma bond, which is represented as this. But we can see with that for carbon to carbon double bond, you have one sigma bond and a Pi bond. While for triple bond, you have one sigma bond and two Pi bonds. But for certain compounds such as the benzene ring, these Pi bonds are not stable, so they tend to move from one position to another. If, for instance, you want to consider a benzene ring structure, it can actually be drawn in two ways. Your benzene ring, and also don't forget the formula for benzene is C6H6. I'll later explain the structural form of this, like the skeletal structure. But for overview knowledge, you have your benzene ring like this. Now, a Pi bond could either be here for this ring or on this other side for the other ring. You could also have a Pi bond here for this ring or on this other side, or here or here. Now, this phenomenon is what represents resonance, whereby a structure could have two resonant forms where the Pi bonds keep changing their positions from the one side to the opposite side, just as this, from here to here, from here to here, and from here to here. Now, resonance is represented by this symbol. And the first resonance structure of benzene was discovered by August Kekulé. This was the person that discovered resonance. Then also, it is not only benzene that has resonance structure. You have other aromatic compounds which involve your phenol. You have other aromatic compounds like anthracene, naphthalene, and so on and so forth, that they all have resonance structures. And like I said, I was going to draw the skeletal structure for benzene. You have it as this. Then you have 6 hydrogen atoms. Now, like I said earlier, due to resonance, you could either have your Pi bond here or on the other side. But you should know that for each Pi bond you place, the amount of bonds for every carbon atom should be 4. So for this carbon atom, you have 1, 2, 3, 4. While this one also has 1, 2, 3, 4. So you can't place a bond here. You have to place it on the next one. So it has to be here. Then you count the bonds for this carbon atom. So it's 4. For this one, it's also 4. If you place a bond here, this one becomes 5, which is wrong. So you have to place it here. Thereby, you have completed a structure of benzene. But now it can also be switched into this, and this. This explains the resonance structure of benzene. And like I said, resonance structure can be represented by this symbol. And the first structure was discovered by August Kekulé. Now, the major function of resonance is to bring about stability in any aromatic ring. You know, we all have different types of hydrocarbons. You have aliphatic ones, which are the straight chain hydrocarbons. Then under aliphatic, you have cyclic, acyclic, you have saturated, unsaturated, and so on and so forth. But aromatic ones are the ones that have the benzene ring structure. So all aromatic hydrocarbons all undergo resonance. Now, the major function of resonance is explained by the resonance theory. So this theory now explains that the higher the amount of alternative arrangement of Pi bonds, the higher the stability. What it's trying to explain is that the more you can alternate the position of pi bonds, the more stable a particular aromatic compound is. Like for instance now, benzene can only be alternated into two forms. Like I mentioned earlier, it can either be alternated as this or this. But then you have other aromatic structures. Let's consider naphthalene for instance. This is what naphthalene looks like. It has two benzene ring structures. Now, the amount of delocalization that this naphthalene has is more than 2. It has 3 resonance structures, whereby you have one like this, then you have another structure like this, while you have the third structure. Sorry, don't mind my diagram. Like this. So these are the 3 structures of naphthalene. Now this now explains that since naphthalene has more resonance structures than benzene, which has just 2, that means that naphthalene will be more stable than benzene. So that's what your resonance series explained, that the more alternative means of arrangement of any aromatic ring, the more stable it is. Now I'm going to give you an assignment or like a classwork to consider anthracene. Anthracene has 3 benzene rings, like so. But then the fact that it has 3 benzene rings, it makes it has 4 different resonance structures. So you should try as much as possible to draw the skeletal structure out and find out the 4 different resonance structures that anthracene will have. Now, because remember that anthracene has 4 resonance structures, to be more stable than naphthalene, which has just 3, and naphthalene will be more stable than benzene, which has just 2. And also another method we use to represent benzene is this. You've seen this very common everywhere. Now the reason why there's a circle in between is to show you that this aromatic compound is always undergoing resonance. That means the pi bonds are always changing positions. So this basically just explains your whole topic of resonance, which is very brief. And like I said, if you want more detailed learning on our A-level program, you can visit Lankotheory Educational Service Limited. You have the contact phone number there, and then we also have the website streaming underneath this video. So without much said, I'll move into my next topic, tautomerism. Okay, like I said, now moving to our next topic, tautomerism. Let me write this properly so you can see it properly. So this is tautomerism. Now, like I said, tautomerism is actually similar to resonance in the fact that both of them involves the movement of pi electrons. Remember I mentioned that for every pi bond, there are 2 pi electrons that forms them. If, for instance, you are considering a carbon-to-carbon double bond, let's say, for instance, in alkene, all alkenes, you know all alkenes have carbon-to-carbon double bond. That's their characteristics functional group. Now, let's assume for this compound, the amount of pi bond is just 1, like I mentioned earlier, and 1 sigma bond. But then the amount of pi electrons now are 2. Because for every pi bond, there are 2 pi electrons. Now, that is the major similarity between resonance and tautomerism, the movement of pi bonds or pi electrons. Now, to define tautomerism, tautomerism is a type of isomerism whereby the isomers exist in dynamic equilibrium. Now, because of that word equilibrium used, that means that tautomerism can be represented by the chemical equilibrium symbol, which is this. That's showing that the rate of forward reaction is equal to the rate of backward reaction. So tautomerism is characterized by 2 things. For instance, you know resonance, like I mentioned, resonance is characterized by just the movement of pi electrons from one point to an alternate point. But for tautomerism, it's the movement of pi electrons from one carbon atom to another, which completely changes the structure of the tautomer. So the 2 compounds, the one in front and the one at the back, that's the product and the reactant, they now exist in dynamic equilibrium, and then they have the same molecular formula but different structure. So therefore, tautomerism needs the formation of isomers. Now, like I said earlier, what characterizes tautomerism is change in position of pi electron and change in position of proton. So that is just the major difference between resonance and tautomerism. Resonance only involves change in position of pi electron, while tautomerism involves both change in position of pi electron and change in position of a proton. And don't forget, it's represented by this symbol, while resonance is represented by this symbol. Okay, now there are two major types of tautomerism. The first one, the basic one, is Keto-Enol Tautomerism. Now this word is gotten from ketone and alcohol. We all know that ketone can also be referred to as alkanone, and the functional group for this is what? CO, and general formula is RCOR, where the alkyl group in front and back would be the same or different. While this enol here represents alcohol or alkanol, and then the functional group for this is just OH, and general formula is ROH, where the R represents an alkyl group. Now, the first type of tautomerism here, keto-enol, just basically means the conversion of a ketone functional group into an alcohol or an alkanol functional group. Then the second and the last one is known as lactam to lactim tautomerism. This tautomerism basically just involves two compounds, lactam and lactim. You see the structures later on, but let's begin with the first type of tautomerism. So I'm going to consider the first member of the ketone functional group. The very first member of the ketone functional group is propan-2-one, whereby, remember that I said the general formula is RCOR. Now, when the smallest and the very first member of the alkyl series is CH3, which is formed from removing one hydrogen from methane. So when you have CH3CO, CH3, this gives us propane. That's 1, 2, 3. Remember, when you have a carbon as part of your functional group, it is counted as the longest chain. So the longest chain here is actually 3. That's propane. Then the functional group here is on carbon 2. So propan-2-one. This is the very first member of the ketone series. Now, we are going to now convert this to an alcohol product using tautomerism. So I'll now draw the structure so that it is seen properly. C double bond O, CH3. And remember that this process occurs in dynamic equilibrium. This represents tautomerism. Now, like I said, tautomerism is also represented as change in pi electron and change in position of proton. So the first thing that changes is the position of the pi electrons. Now, if you look at this whole chain, the point where you can locate the pi electron is here, because this is the double bond. Remember when I said carbon to carbon double bond has a sigma and a pi bond, sigma and pi bond. So definitely among these two, you have a sigma and a pi bond. So the first thing that happens is change in position of pi electrons. So you have the pi electrons move from here to here. That means they've been converted from this carbon here to this carbon. Then we'll draw a structure for that. You now have CH3, C, remember one pi bond has been lost from here, so you have just one sigma bond, oxygen. The pi bond moved down here, so it's now double bond, then CH3. Although this is not the final structure, this is showing mechanism, called mechanism of reaction, where you show the steps you use to get your answer. So when this happens now, oxygen is used to having 2 electrons. Remember that oxygen is 2,6. That's its electronic configuration. It is used to having 2 electrons to complete its octet structure. But because it has lost one, it becomes O-. And usually, carbon is used to having 4 bonds to complete its structure. But now it has excess, which is 5. 1, 2, 3, 4, 5. So it becomes highly electropositive. Now, because of the high electropositivity of this, it wants to give out hydrogen. Remember now I said proton. Proton is represented as H+. That is a hydrogen proton. So because this is very electropositive, it will give out a proton and therefore complete the process of tautomerism. So this hydrogen atom moves from here to this oxygen. So our last structure will now be given as